In this video, we're going to be looking at some of the antiderivative rules for things that you can't use the reverse power rule for, such as trig functions, e to the x, and 1 over x. So at first, this is just going to be quite a bit of notes. I'm going to give you the definitions. You're going to add them to your notebook. You won't need to memorize these for the exam. I'll provide them to you in one form or another. But for now, you do want to add them to your notes so that you can use them while you're working on the exercises, and also so you know what to use and when to use it. So the first things we'll do is just list all the trig functions and their antiderivatives, starting with the antiderivative of sine ax dx. And a is just any number. Usually that's a 1, and then you just have sine x, but it could be sine 5x or sine 10x or whatever. And the antiderivative of that is negative cosine ax over a. And then, of course, we have our plus c. The next one we'll have, and we're just going to work through all of these, cosine ax dx with respect to x, of course, equals sine ax over a plus c. And these should make a little bit of sense to you. Remember, the derivative of sine is cosine, so it makes sense that if you're going backwards, cosine would turn back into sine. These are just coming from the derivatives, just kind of working backwards. Okay? We have secant ax tangent ax dx. It's kind of a lengthy one. And this is just equal to secant ax over a plus c. Then we have the antiderivative of secant squared ax dx is equal to tangent ax over a plus c. We've got a couple more to do before we actually show you how to use them. We could do cosecant ax times cotangent ax, all of that dx, all this with respect to x, and that just turns back into negative cosecant ax over a plus c. We've got one more. It's not a very good integral sign, but we're just going to go with it. So the antiderivative of cosecant squared ax with respect to x will be equal to negative cotangent ax over a. And once again, you're not going to need to memorize all these. Of course, you're going to get a little bit faster with them the more you use them, but I'll provide these to you in one form or another. It just helps to know that, that what these are and that they all exist and when to use each one. Let me go ahead and include each of these in parentheses just so you know that the dx is never really part of it. The dx is not part of the integrand. That's the variable of integration that's required for taking the antiderivative. We've got two more we're going to look at, and the first one is the antiderivative of e to the x with respect to x. And you might remember that the derivative of e to the x was e to the x, so it should make sense that the antiderivative of e to the x is also e to the x plus some constant. And then we also have the last one, which is 1 over x dx, and this one's special. This one turns into natural log the absolute value of x plus c. All right, let's look at a couple examples. Let's first look at the antiderivative of sine 5x. And if we look back at the identities that you just wrote down, hopefully, this one would turn back into negative cosine 5x over 5 plus c. Let's look at another one. Let's do cosine pi x dx. And this one, looking back at the identities, you'd get sine pi x over pi plus c. Okay, let's try a different one. Let's look at cosecant squared just x dx. And this one, notice I didn't write anything in for a, So if we want to, we could put in a 1 just as a placeholder, but actually it's not going to make that big of a difference. It's just whatever would go there is just going to be a 1. So it's just going to turn into negative cotangent x. Once again, there's nothing here for a, it would be a 1 over 1 plus c, and then we'll just simplify that. Since it's being divided by 1, we would just write negative cotangent x plus c. These also get more complicated in the exact same way as in the last video we watched, where if you have them separated by addition or subtraction, you can really just rewrite this as separate integrals. So you can write this as 2 secant squared x dx as its own integral minus 5 cosecant squared x dx, and that is its own integral as well. Then the constant, we can always just bring that outside. So we have 2 times the antiderivative, or the integral of secant squared x dx minus 5 times the antiderivative of cosecant squared x dx. Then we can take the antiderivatives using the rules we just talked about, and we're going to have 2 times tangent x plus 5 cotangent x plus c. And in this case, it's a lot simpler because there's nothing in here for a. It's not like secant squared 5x. It's just secant squared 1x. So the antiderivative will just be tangent x. The last one we'll look at will just be an example with e to the x. Once again, this is e to the x divided by 12. This requires a quick rewriting of what's going on here. It's really like 1/12 times e to the x dx. The antiderivative of e to the x is just e to the x, so we're just going to have 1/12 e to the x, or e to the x over 12, plus c.